Good day, everyone. Today we are going to be taking a look at section 4-4, which is all about friction. Now, friction is a quantity that we've used before, and it's a quantity that we're familiar with in our everyday lives. Friction is all around us. Anytime we are moving or trying to move something, or even just coming into contact with something, friction appears. So friction is a quantity that we are all intimately familiar with, but now our goal is to put it into better terms, to quantify it and get a deeper understanding of how we can quantify and calculate the friction on an object. So first of all, let's begin by formally defining what friction is. Friction is a type of force that is classified as a resistance. A resistance force is simply a force that opposes motion. So the direction of friction is rarely given to us in a problem because it's always assumed that we can predict the direction of the friction because it's opposite of the motion. So if we are attempting to move an object to the right, friction will automatically go to the left, and so on. Now, friction is only going to occur whenever an object is against a surface. So if you are pushing an object across a table, across the floor, moving something up a ramp, or holding something against the wall, those are all surfaces. However, when something is airborne, then the object will not incur any friction because there's no surface for it to be in contact with. Now, this piece right here is very important for us to remember about weight and friction. Friction is not due to an object's weight. Friction is caused by an object's normal force. So this is a very important thing to bear in mind. Many times, weight and normal force are going to be equal and opposite to one another, but not always. For instance, if you press an object into a wall, the weight goes straight downward, but the normal force is going to be pointing perpendicularly from the wall. In that case, it is going to be different than the weight and the normal force are going to be different from each other. Now, the other quantity that we're going to need to know is this new term called the coefficient of friction, abbreviated by the Greek letter mu. That is this U-shaped letter here with the little tail on the front of it. All surface-object pairings have a unique coefficient of friction. So, for instance, rubber tire against pavement has one coefficient of friction. Rubber tire against wet pavement has a different coefficient of friction. Rubber tire against ice has a third coefficient of friction, and so on and so forth. Mu is unitless, and it's never greater than 1. You can never have more friction than the object would have on its own. And I'll get to what that means in just a moment. What the mu represents is effectively how much grip there is between the surface and the object. And we calculate friction with this formula right here. The force of friction is equal to the coefficient of friction times the normal force. Now, this is the only formula where we can arbitrarily add or remove negative signs because friction and normal force are perpendicular to each other, so we have to assign their directions once we are ready to do so. So now, it's important for us to consider that there are two types of friction: static friction and kinetic friction. Well, static friction depends on the object being at rest, and kinetic friction occurs when the object is moving. So this is an either-or scenario. An object will have either static friction or kinetic friction. It cannot have both of them. Now, friction will change depending on whether or not the object is moving. As I said, if it's moving, it's kinetic friction. If it's not moving, it's static friction. If the object goes from rest to moving, it goes from having static to kinetic. Now, the reason we observe two types of friction has to do with the inertia of the object. When something is not moving, we have to overcome its inertia in order to accelerate it and get it moving. The inertia effectively works against us and aids the friction. While when something is already moving, its inertia works with us and wants to keep it moving. Luckily, we calculate these with the exact same formula. Friction equals the coefficient times the normal force. The only difference is which subscript we give the coefficient of friction. Excuse me. An S if it's static, and a K if it's kinetic. And it's important for us to note that static friction is always the stronger version of the friction, because it's more difficult to get an object moving than it is to keep it moving. It's important to note, however, static friction can never be greater than the applied force on an object, but kinetic friction can, and that can be somewhat confusing. So now let's get into some examples. Our first example asks us to calculate the amount of friction from a coefficient of 0.23 and a normal force of 200 newtons. So let's give this a try. First of all, this is our coefficient of friction. We know that's the coefficient for a couple of reasons. The first being is that the problem calls it the coefficient. The second is that it's unitless. The coefficient of friction is the only quantity that's unitless that we're going to be working with. So if you ever see a unitless decimal, that's going to be our coefficient of friction. And then we're told we have a normal force of 200 newtons. Well, friction, the force of friction is the coefficient times the normal force. So this problem, luckily, is just a plug and chug. 0.23, no unit, times 200 newtons. Then do we just go to our calculator? 0.23 times 200. 46 newtons of force. And note that the unit is still in newtons. We have newtons here multiplied by no unit, so therefore it stays in newtons. Problem 2 reads, calculate the coefficient if there is negative 34 newtons of friction and a normal force of 148 newtons. So here, we're going to take a look at what we have. 34 newtons of friction and a normal force of 148. Friction equals mu times the normal force. I dropped the capital F's in this case because we're only working with friction and normal force. So F and lowercase f and capital N are clear indicators of those. So to get the normal force away from the coefficient, we have to divide it on both sides. So mu is friction divided by normal force. We're going to drop the negative because the coefficient doesn't have a direction associated with it. And again, this is the only formula where we can simply drop negative signs. Note the units of newtons cancel out entirely. 34 divided by 148 gives us a coefficient of 0.23. And that's it. So this one is a connection problem, which means it's going to tie back to previous material that we've had before. We're going to see these problems pop up now and again. They are a little bit more challenging. Excuse me. They are a little bit more challenging because we're dealing with multiple steps to these problems. So the first step is always the same. Read the problem first. If a 35 kilogram crate is pulled forwards at a constant velocity, determine the amount of friction if the coefficient is 0.22. We got a lot of information in this problem, so first let's write down what we know. We know that the mass is 35 kilograms. We know the coefficient of friction is 0.22. Numerically, those are the only two numbers we're given. But we know that it is moving at a constant velocity. That means that the acceleration is 0, which by extension means that the net force is also 0. Now, our next step is to draw a free body diagram, because in this case, we don't have the normal force to calculate the friction. So we're going to have to solve out for one of them. So here's our crate. We know it's being pulled forward with some unknown applied force. The unknown friction goes backwards. The weight goes straight down. That's mg. And the normal force goes straight up. Now, we have to sum out our forces. Applied force minus friction equals the net force, which is 0. And normal force minus weight equals the net force, which is 0. So now we have what we need. Normal force is equal to mass times gravity. For the sake of simplicity, I'm going to round gravity up to 10 meters per second squared. And we see that the weight is 350 newtons. And so now we can get the friction. The coefficient times the normal force. 0.22 times 350 newtons. 0.22 times 350, plug that into your calculator. There are 77 newtons of frictional force present. Final example here. Once again, this is a connection problem, so we have to think a little bit more about what else is going on. The coefficient of friction between rubber and pavement is 0.27. If a 980 kilogram car's engine applies 3,000 newtons to move it forward, what will the acceleration of the car be? So this one's a little bit more complicated than the last one. But we want to apply the same logic. First step, the givens. The coefficient is 0.27. The mass is 980 kilograms. And we know that the applied force is 3,000 newtons, because that's what the engine applies to move the car forward. The next step, draw our free body diagram. It's actually going to be identical to the last one we drew. And so what's nice about that is that our net force equation is actually going to be virtually identical. The only difference is that in this case, the net force is going to be mass times acceleration in the x direction. In the y direction, it's still going to be 0. It's going to be 0 in the y direction because if we think about the way a car moves, it only moves horizontally. Cars, unless there's some real fatal flaw in what you're doing with it, are really bad at going vertically. Hopefully. So once again, we can solve out for the normal force, which is equal to the weight, rounding up gravity to 10, 9,800 newtons is the weight of our car. Now, 9,800 newtons of normal force will allow us to get the friction. 0.27 times 9,800 newtons plug and chug. (2,646 newtons of friction. Now we are in the home stretch of this problem. We now have to solve for the acceleration. And we're going to go back to this equation right here. Because we know the applied force, that's 3,000 newtons. And we're subtracting the force of friction, 2,646 newtons. And that's equal to m times a. So the left-hand side, 3,000 minus 2,646, is 354 newtons, equal to 980 kilograms, that's our mass, times the acceleration. Dividing both sides by the mass will give us the acceleration. Comes out to be 0.36 meters per second squared.